Welcome to the 20th video of this course on quantum processing. Today is a quantum field theory problem, simulating quantum simulation of ultra-cold atoms and optical lattices for studying the Anderson-Higgs mechanism. When I first even wrote down this title, I forgot to add Anderson. So Anderson should not be forgotten, like many physicists actually do, that they forgot to add Anderson in this Higgs problem, but Anderson was a substantial contributor, is a very important contributor in the development of quantum field theory maturity, and you'll see in a second why this is important for Anderson. So this video is built upon the fact that you know the basic introductory part of quantum field theory, at least the basic equations that correspond to this Lagrangian. I didn't write down this to intimidate you, but I recommend if you don't know the basics to follow this video is to check them out from any recommended textbook, Weinberg for example, to appreciate the glory of this quantum simulation problem. So this Lagrangian is nothing else than the covariant derivatives here for the leptonic field, and this is the gauge field for the electromagnetic field here part, and the tensor for F capital here. So you can transform this to smile if you know the Lagrangian. And let's get into this Lagrangian, the simplest relativistic field theory that we can get for this derivative here. So remember that this is the kinetic energy and this is the potential energy terms, and you have also this for self-interaction term. This is coming from massless Dirac Lagrangian and lambda phi 4 theory for quartic interaction. And remember also that we build this to include that the mass is negative here. So we include the mass is negative in order to plot this function that looks like this. Potential energy function for this v of phi. So you in fact saw this before in quantum field theory courses. This is a Mexican head potential, okay, and you have infinite ground states around the rim of this Mexican head potential, and now we would like to break the symmetry. This is spontaneously breaking symmetry problem, and remember also that the Higgs mechanism is equivalent to the Maxwell's theory when you add this important spontaneously breaking symmetry structure. So we have the infinite vacuum states around this rim here. So the minimum, we would like to pick one ground state and to excite this ground state and to ask what is the excitation when I pick this, when I break this symmetry and select one mu, say mu, this is the point that we're going to excite around, and we have, sorry, this is for phi square, this is the minimum point here for this mu expression here. We can write down this phi as for the two orthogonal scalar fields for phi 1 and phi 2, and you add this minimum ground state point that we are going to select upon the spontaneous breaking symmetry structure. So we can write down also, if you are familiar with this structure from the Higgs mechanism, you can fully recover here this expression. So we can write down now the potential energy function of the scalar field that looks like this field. Okay, from here. So this includes the mass term inside it. And remember that this is for the infinite structure, for the infinite ground state around this rim. This is a problem of which is global symmetric U1 problem. So this is a U1 symmetric problem for this field that you can evolve this for exponential for this phase. And remember also when you write down this phi, dagger phi, it's equivalent to half of this summation for this in order to fully get this equation for the potential energy. And then you ask what is the Lagrangian of the system now when I introduce these important concepts or important equations to substitute and to get this Lagrangian of your system here. Okay, so this Lagrangian is kind of important, and it includes now here this term, which includes the mass inside it. Let's pick phi 1 for example, and this term is actually a massive term. Okay, let me just write it down. This is a massive term, and this is for the massless term, doesn't include mass, and here it's called the Goldstone mode of your system. Actually, it's called the Nambo Goldstone mode. So here the Nambo Goldstone mode, this is the massive term, and this is the massive term which corresponds to the Higgs amplitude mode here. Here in our system, in the condensed matter problem, the Goldstone mode is nothing else than a phonon mode, the sound waves, for example. Okay, it's massless, and now we have the massive term that includes the mass inside. This is the Higgs problem, the Higgs amplitude mode that you can find here for this Lagrangian system. So let us indicate important facts that we will do in this Lagrangian in order to develop it in a more mature form. Remember the global symmetry, we encountered the global U1 field symmetry here for everywhere. So the ground states are all the generated ground states. And you have the local symmetry. Now we would like to pick this local symmetry problem, and we would like to extend to this symmetry structure. So we will introduce a vector potential. Okay, we'll couple this to vector potential in order to allow this theory to be gauge invariant along the unitary transformation here. So for this problem to be gauge invariant and under local symmetry U1 field transformation, we have to add this vector potential term here, and you have to minimally couple it to this covariant here system affecting for the scalar field, and then you couple both. You include the vector potential, you include the coupling to make it a nice theory, and then you the spontaneously breaking symmetry behavior again you do, and then you write down this Lagrangian system here. So let me remind you that you can write also down this Lagrangian. I'm sorry if this is not clear here. So we can write down this Lagrangian before introducing the other Lagrangian as T here for, okay. Okay, this one here. Yeah. For this field tensor. And this is the potential. So remember that we can have this Lagrangian that looks like this. So upon spontaneously breaking symmetry, you will evolve this to this important Lagrangian here. So this is the most important Lagrangian that you can see today. Okay, why? This Lagrangian includes the massive term and this vector potential. Okay, so this now becomes a very massive term. This is a massive term for this is corresponding for the photon field. Now the photon are massive, and for this phi 1 and phi 2, now the Goldstone mode can disappear once you just pick a vector potential that would vanish or would kill this term for phi 2 square here. Now you have the massive term corresponding to the massive photon field, and this is exactly what I told you about the contribution of Phil Anderson when he suggested the 1960 paper about this. He encountered this for the Meissner effect in condensed matter, that this is exactly what he proposed when he said that you have a term which is massive term here corresponding to Meissner effect in condensed matter problem. So Anderson's contribution to that was substantial, and we have to know about it here. So this Lagrangian is a nice Lagrangian now that you can get upon spontaneously breaking symmetry here. And remember that this is for the electromagnetic field part here also, and this is the other parts corresponding to extensions that we have in our Lagrangian.